All right. Again, good morning, good afternoon. This is Matt with ATA. I think we'll get started here. I think we have most folks that registered online and maybe a few more will trickle in and we can continue with them as they come online. So again, this is Matt with ATA. I'm in the Midwest. I'm a business development manager on our test side, helping to cover um, our value-added reseller business with Siemens on test hardware and software. So I'm excited to kick off just a quick high level on ATA and then pass the keys over to Gabriel Cruz, who's going to take a deeper dive on today's topic of digital signal processing. So
Perfect.
just to give a high level on what we do, we're a test design and analysis engineering services company that's been around for more than 4 decades, back in the 80s, and then up until early 2000s. We branched off and continued our engineering services and deepened our partnership with Siemens in the early 2000s and to date. Primarily, our focus is in areas that you can see here is defense and aerospace, spacecraft, as well as some heavy equipment, industrial mining, and pretty cool as well as themed entertainment. Um, a bit more about who we are as a company. So we're an employee-owned company, with everybody having a vested interest in the company and providing extreme customer delight. And we're all very passionate engineers and business development experts in this area. Today we have well over 200 staff, many with advanced degrees up into the doctoral PhD level, focused in many core areas today within like thermal and hypersonic and structural analysis. Um, so that's a bit about who we are. We're headquartered in San Diego with multiple locations across the country. A bit about our services. Again, I'd mentioned design, analysis, and test. We're deeply interwoven in all three of these product development areas. We're able to support our customers, whether it be on site, um, in classified type work and in secure areas as well as not, and across all three disciplines, design, analysis, and test. We have multiple test labs, with our largest being in San Diego, and so we're well poised and expert to supporting customers both remotely and on site across a wide discipline of teams. Again, a bit about our software and hardware services. So, as I mentioned, back in the early 2000s, we became a reseller for Siemens. This started back with NX, Nastran, and FEMAP. We do a lot of training and help on the development side with that software solution. And as well, recently we became a value-added reseller about 4 to 5 years ago on the testing side, which we're going to talk a bit more about today. We also have our own suite called ATA Suite, which can augment Siemens software simulation and test tools and its methods that help speed up and increase your engineering design and analysis productivity. So I think with that, I'm going to pass it over to Gabriel Cruz, who I'm excited to have here. He recently joined our team on the test and software and hardware side, and he's going to take us through a bit more about digital signal processing. Over to you,
Awesome.
Gabe.
Thank you, Matt. Let's get into the agenda for today's presentation. So I'll give you guys a brief introduction into digital signal processing. Then we'll go over what is a Fourier transform and the FFT that we're going to be doing. We'll go over some brief signal analysis examples. How do we actually apply what we learned about the FFT to the measurements that we take? We'll go over some basic parameters going over windowing and leakage. I'll give you guys a conclusion and then I'll give you back the rest of your day. All right. So, why do we actually care about digital signal processing? So, with digital signal processing, I think a lot of us have the digital part down and the processing part down. But what is a signal? A signal is a measurable quantity about some physical phenomenon. So, you have something that you want to measure. For the in the context of noise, vibration, and harshness, there's a lot of different things that we can measure. So one of the things that we can measure is, let's say, acceleration, utilizing an accelerometer. Um, some other things that might be more important to, let's say, this is accelerometers mainly for vibration. If we're looking at acoustics, maybe we want to utilize a microphone, which measures pressure. And then finally, if we're maybe looking at some durability, maybe we want to analyze strain. So all of these relate back to some physical phenomenon. Let me get out the laser pointer. So all of these measure some physical phenomenon. But what do they all really have in common? In that all of these devices output some voltage. So there is some mechanism inside of each of these devices that modulates some output voltage that correlates to some physical phenomenon. So there's a level of abstraction here that this doesn't quite measure acceleration, pressure, strain in the way that you think, but it's just the modulation of this voltage. So if we look at the internals of a microphone, which is very similar to the internals of an accelerometer, minus this diaphragm piece, but there's two main pieces that we're really interested in. This center electrode is supplied with some constant voltage level. And then this diaphragm piece vibrates up and down. With the vibration of this diaphragm, there is some component in here which acts as a capacitor. So as this is vibrating, it is going to change the capacitance in the circuit, which modulates the voltage, which is going to end up looking something a little bit like this. So this right here is some data that I took in the time domain. So if you just took any sort of microphone reading, you might get something that looks a little bit like this. And the context of noise, vibration, and harshness, there really isn't much that we can extract out from this data. I can see here that this is over the course of 15 seconds. This is taken from some time from a longer recording. And I can see what my pressure readings were on the microphone. But if I'm trying to analyze the acoustics of this part, well, I want to know what frequencies make up the sound that I'm hearing. We know that sound is the combination of all of these wide different frequencies. So we need some better representation than this for the purposes of analyzing for NVH. And so what we want to do is convert this time domain data into the frequency domain data. So we want to look at what components are making up this signal. So how do we actually do that? So we start with our input time domain data. So if you're doing, let's say, a frequency response function, you're performing your modal analysis, you're going to get some data that looks like this. If you're utilizing, let's say, a modal shaker, if you're using an impact hammer, it's going to just be an impulse for this input, and you're going to have some output right here. What you're going to do is, in order to go from the time domain to the frequency, you're going to compute an FFT linear spectra. So we can say that a spectrum is just essentially your frequency domain data. So we can see here we're going from time to frequency, but we have this step right here, which is going to be extremely important, the computation of this linear FFT spectra. So how do we actually do that? Well, we can thank Jean-Baptiste Fourier for his Fourier transform. So the Fourier transform, maybe you learned this in calculus too, but what it allows us to do is represent any function as a series of complex numbers. So we can see down here, these are the two main formats that we're going to be using. So right here on the left, this is the one that you're probably familiar with from calculus, which is the Fourier transform. But in the context of noise, vibration, and harshness, we're going to be utilizing a slightly different formulation. We're using the FFT, the fast Fourier transform, which is based on this equation right here on the right, which is the discrete Fourier transform. So all discrete means is that we have data points. So if we have a certain amount of data points, we can utilize this DFT and kind of create a summation of our function utilizing complex numbers. But for myself personally, I really don't like this complex formulation, e to the negative I x essentially. I really don't like this formulation. So can we have any alternative formulation or way to represent this equation that is a little bit more useful than this? So I like to utilize this rectangular coordinate form to explain noise and vibration because when we're looking at this equation, there are two components here. We have this real component and we have this imaginary component. So let's progress through the slides. So this imaginary component, we can see that it has this I right here. So if we can think, this is essentially a unit circle, for example, with this real and imaginary component. And on the inside of these trigonometric functions, we have this varying zeta x term. And so we can say that the FFT is essentially taking a summation of a bunch of different, essentially, if you're varying this zeta x, all of these are going to be different frequencies. So you're summing up all of these different frequencies in order to match a signal, to match your input or your output signal. So if we take a look, if you're familiar with this sort of S omega curve, you have your real and imaginary. So when we're looking at the FFT results, you're probably a little bit more familiar if you're utilizing Bode plots with amplitude and phase. But the amplitude and phase are coming from these real and imaginary components. And so, what we really gain from this is that the FFT allows us to go from the time domain to the frequency domain with the summation of all of these different trigonometric functions. And so there's a lot of different important relationships that go into performing your FFT and taking your FFT and doing all of that analysis. The most important function that we're going to be looking at probably is this Nyquist-Shannon sampling theorem. So this is your band limit, aka the maximum frequency you can analyze, is equal to 1/2 of your sampling frequency. So the Nyquist-Shannon sampling theorem determines the maximum frequency we can analyze. But there's a few other more important equations here too to your FFT. So these are two different representations of your frequency resolution. So what is the resolution of your spectrum? So looking at this bottom equation right here, this is your Rayleigh criteria. So we can see that our frequency resolution is equal to 1 over the time block. So if we're measuring for 1 second, we can expect to see data points every 1 hertz. So we could see 1 second, 1 hertz, 2 hertz, 3 hertz, so on and so forth. If we're measuring for 2 seconds, now we're seeing a frequency resolution of half a hertz. So zero point 0.5, 1, 1.52, so on and so forth. This is maybe if you're utilizing TestLab Neo, you're a bit more familiar with this Rayleigh criteria. If you utilize TestLab Classic, you're probably a little bit more familiar with this middle representation of your frequency resolution, which is the bandwidth divided by the spectral lines. So the most important equation right here, though, is probably going to be this time block one, which we'll actually discuss about a little bit later. But kind of looking at these two equations right here, I have band limit versus band width. Why do I have two different metrics right here when we're saying, uh, okay, cool. Just had to make sure that my microphone's still working. So band limit versus band width. Do we always want to set our band width to our band limit, which is half our sampling rate? And I'll actually show you maybe why you may or may not want to do that. So we've got this figure right here. So this is showing some signal that is being generated and then some signal that we are measuring. So this Fs is our sampling frequency right here. And then right here, this Fs over 2 is our band limit. So half of our sampling frequency. So we can see that this top graph is the signal that is actually being generated and what we're actually seeing. And as we approach that half of our sampling frequency, our measured signal does not look like the signal that we're actually seeing. It looks like it's actually lower in frequency than we're actually seeing here. And so this is a good visualization of the phenomenon known as aliasing. So aliasing is when a frequency higher than our band limit is present in our signal and appears to be folding back in on itself with this lower frequency. So how does that actually appear when we're doing our FFT analysis? So you'll commonly see this when you're performing your color map as you're approaching your band limit or your bandwidth on your graph, you'll see it kind of flipping back in and those frequencies kind of representing, I kind of think of as it's bouncing off this wall and getting reflected back in to this end portion of the graph. So we need some ways to go about in mitigating the effects of aliasing when we take our measurements and performing our FFT analysis. And so one of the ways that we can do that is by applying an anti-aliasing filter. And what this allows us to do is measure up to half of our sampling frequency. So what it does, it is essentially a low pass filter. So the difference between a low pass versus a high pass filter, a low pass lets all of these low frequencies through, whereas a high pass would only let the high frequencies through. And so we're applying a low pass filter that starts at roughly 20% of our span. So we can say that the first 80% of our measurement will be filter free. We won't have any reduction in amplitudes due to our anti-aliasing filter, whereas that last 20% are going to have decreased amplitudes and maybe some of this effect from these aliased frequencies. So let's say, for example, in this situation, we're sampling at 2000 hertz. If we really have a component that we care about and want to really know the vibrational effect at, let's say, 950 hertz, well, we're probably going to need to adjust our sampling frequency. Otherwise, we will see a reduction in amplitude due to this anti-aliasing filter. Or if there's, let's say, a high component at 1050 hertz, it could be showing up as 950 hertz in this scenario. So we want to take that into account when we're making our measurements for selecting our sampling frequency. So there's a few different regions where your anti-aliasing filter is applied. There's one performed before you actually do your analog to digital conversion, which is a whole other topic of a webinar into itself, going about when you're actually calibrating your sensors, gain, range, and quantization error. And then we've got another anti-aliasing filter here when we actually perform our analysis. So I've got another slide right here that shows all of the different sampling relationships that are extremely important for your FFT analysis. I'm not going to go over all of these because there's a lot of them. But what the key from this slide is that once you know any two of the parameters in this equation, all of the other three are defined automatically. So we won't spend a lot of time on this, but this slide is so beautiful. I would set this as my home screen background. So you would always have these equations ready to go. So we kind of went over sampling frequency, bandwidth, and frequency resolution as the roles they play into our FFT analysis. And that middle equation on that last slide, we were talking about spectral lines and bandwidth and frequency resolution. So essentially, spectral lines are the amount of data points that you have in your FFT on your spectrum. So, but what is extremely important about your spectral lines is that they aren't the exact value at a specific frequency. So, like I said, if I had a 1 second time block, I would have a frequency resolution of 1 hertz. So we'd have spectral lines at 1 hertz, 2 hertz, 3 hertz, 4 hertz, so on and so forth. But that spectral line encompasses the amount of energy in between 0 to 1 hertz, or a little bit between that, maybe around 0.25 to 1.2, so on and so forth. It is encompassing a range of energy and not actually the frequency itself. So then that kind of begs the question then, well, why don't we just use the greatest frequency resolution and then the most amount of spectral lines? Well, let's see why. So I'm going to show you guys some analysis with the basic 400 hertz sine tone. If we were to take the FFT of this signal, what would we expect to see and what are we going to get? So we're going to examine it utilizing three different frequency resolutions. So we've got a 4 hertz signal, a 1 hertz signal, and then a 1.7 hertz signal. So classically in literature, if we were to take an FFT of this time block, so this is a 5-volt sine wave at 3 hertz, we would expect to see in our spectrum at 3 hertz just a line that appears with an amplitude of 5 volts. So this is a 1G, in this example, it's a 1G sine wave at 400 hertz. And we're pretty zoomed in right here. So we're looking over the course of 370 to 430 hertz, but that's pretty close to what we see here. It's essentially just a line appearing at 400 hertz. But when I look at this graph, it kind of looks like our 4 hertz resolution, which is this blue line. The red is our 1 hertz, and then the green is this 1.7 hertz. It kind of looks like the blue has a bit more energy. The instinct is to say the blue has the most amount of energy. It has the greatest area under the curve. But area under the curve, when we're looking at this auto power spectrum, is not exactly correct. And I want to show you when we look at some alternative representation here. So I want to show you what this looks like in a block view. So this is showing the energy at each of the spectral lines. And it looks like if we're looking at our 1 hertz resolution and our 4 hertz resolution, if we were to look, they have the exact same shape. They have this one spectral line with this much energy, and then these two other spectral lines have the same amount of energy. So we don't compare energy based on area under the curve. If we're kind of trying to do, let's say, a graphical representation of our energy component, it would be actually stacking up these blocks and looking at the height. So if we were to stack up the red and the blue blocks, they would have the same height. Same if we were to stack up all of these green blocks down here. It's just a little bit more tricky to visualize that. And one other factor that I wanted to mention too. So when I said earlier that the spectral line encompasses the amount of energy at that frequency, what do I mean? So we're looking at a 400 hertz signal right here, right? If we were to now, let's say, do two different frequencies, one at 399 and let's say 401 hertz, the blue graph does not have enough resolution to kind of pick out those two frequencies. So it would be actually summing them all up together. We would see one really big blue peak, whereas with our red curve, the red curve would actually be able to determine the difference in those two frequencies based on our resolution. So we might have two peaks, one at 399, one at 401, that would be half the size of the peak of the blue one. And so I want to show you guys how we can actually go about and calculate the energy content in this graph utilizing some of the display features inside of TestLab, or not inside of TestLab because we're not in TestLab, but utilizing some of our active picture displays. So if you generate graphs in TestLab, which is the Siemens test hardware, they have this active picture PowerPoint plugin. And so what that allows you to do is edit the pictures inside of PowerPoint without needing to go back to TestLab, re-upload the pictures and everything. So right here, I could put a double cursor and we can kind of drag this around and then it tells us what frequencies we're seeing here. If I want to determine the amount of energy that we're seeing on this signal, I just can go down here, put in a calculate on this double cursor, and then determine the RMS of this signal. And we can see that the RMS for this signal is the same for all three, which makes sense because we're analyzing the same signal. We might start seeing some differences depending on where I put this cursor based on the kind of spillage of energy from one band to the other. If we kind of go back to this slide here, there's kind of some amount of leakage out onto this other side. And I can actually show you guys one other example right here. So we're going to get rid of that cursor and I'm going to change up the limits here on this graph. So we're going to go from 0 hertz to 500 hertz. And like I said before, when we're looking at like the analytical example or the graphical example, we would expect to see, yeah, just one peak right here. But what happens when I put this Y on a log scale? What are we going to see? Yep, that seems pretty strange. Probably not what we were expecting. We do see just the one peak for the 1 hertz, the one peak for the 4 hertz, but there's something going on with this green line. We can see that the energy is kind of being distributed all across the frequency range. There is something going on here that is causing the energy to kind of be distributed. I mean, we're seeing stuff in the 200, 300, 350, even into these other side bands over here that the 4 and the 1 hertz aren't even able to see. So what is going on here? So what we're seeing here is the phenomenon known as leakage. So one of the rules of performing a Fourier transform is that it has to be utilized on a periodic function. So a periodic function just means it's going to start and end at the same point every time. So it starts at 0, ends at 0, essentially. So if you don't not utilizing a Fourier transform on a periodic function, you get this phenomenon called leakage. And we can see that here. If we're measuring this sine wave non-periodically, we can see that it's discontinuous at our measurement blocks, at the beginning and end of each of our measurement blocks right here. And so the repeated signal does not look like this one. So before we were looking at a 400 hertz sine wave. With one with the 1 hertz and the 4 hertz, we're able to measure that 400 hertz periodically. That's why we didn't see any sort of leakage out to the other frequencies. And that's why I specifically chose 1.7 hertz because it is performing an effect that looks similar to this at each of the measurement blocks. And so this is the effect of leakage if we're looking at a little bit more of a classical representation. So what we see is if a non-periodic function is captured for FFT analysis, we see a reduction in the amplitude here. So we actually have a less amplitude with our leakage signal, and it broadens the frequency response. So kind of splaying out to all of these other frequencies. So we really don't want leakage. So how can we actually go about and mitigate the effects of leakage on our measurements? Well, one of the ways that we can do that is by applying a window. So commonly in the noise, vibration, and harshness industry, we're applying this Hanning window. And what that's doing is applying this weighting filter where it has zero amplitude at the beginning and zero amplitude at the end. So we're taking this original signal, multiplying it by the window, and getting our new windowed signal, which has zero amplitude at the beginning of the end, satisfying the periodic function requirement. But now what I want to point out is this is what we're now performing our FFT analysis on. This is definitely not the same as this original signal. And what you can see is when we perform FFT analysis on our windowed signal, we still don't quite get to our non-leakage peak right here, but it certainly does look a lot better than if we were to not apply the window at all. And so what I want to say is, and what I really want to hit at is that when we're applying a window, it is still a necessary evil because ideally we would be taking measurements that do not experience leakage at all. They would be periodic, but that is not exactly depending on the case when if you're doing maybe like a pseudo random test, you might actually be able to fulfill this no leakage requirement. But if you're doing, let's say, a random sine sweep, then, well, sine sweeps are actually periodic. But if you're doing, let's say, a random test with a shaker, you're going to have to utilize a window. So some of the effects of the window that the test lab software automatically corrects for is, well, when we have that apply that window, it's going to reduce the amplitude that we're seeing on that peak. And that makes sense because we're pretty much applying a filter that is reducing the amplitude of our signal. And so the software automatically calculates for that. But we can see that the energy is not the same when we apply the window, at least when we're performing analysis in a auto power. So I want to kind of get into another example here, kind of going a little bit more over energy content and what is the levels in our signal. So we're going to analyze this completely random signal. I generated it completely randomly inside of TestLab. So in this random signal, we're going to perform again FFT analysis with different frequency resolutions. So we've got these three different frequency resolutions. We've got a 2 hertz, a 4 hertz, and a half hertz signal. And if I were to kind of ask you on an initial appearance of this slide, which one has the highest overall level, your initial instinct is probably to go with the green graph. I mean, if we kind of go on to this next slide, we could see that the level right here, it's at 0.024, 0.017, 8.47, 10 to the negative 3. So, I mean, when I look at these different graphs, I see, okay, well, if I were to just take an analysis of this, my initial thought is, boom, the green has the highest level. But this kind of ties back to the energy concept from a few slides back. This green graph is encompassing more frequencies per spectral line. So it's summing them all up together. So like if we go back to that 399, 401 example, if there was two peaks at 399, 401, this one would have one really big peak, whereas down here we're having multiple individual lower sized peaks. So utilizing an auto power spectra when we're trying to determine the energy content of our signal is essentially utilizing the wrong tool for the job. What we need is another kind of graph called the power spectral density. So kind of ignore these blue ones. We're going to look at these yellow boxes right here. So this is the formulation for our auto power function. So this is the real and imaginary components of our FFT that we were kind of taking a look at earlier. We're just multiplying itself by its complex conjugate to negate out that imaginary component essentially. And so when we're typically looking at our spectrums, we're looking at this linear auto power function if we really care about the amplitudes of the graph. But when we're trying to determine the energy content, we utilize this power spectral density. And what this is taking that base auto power function and dividing it by your frequency resolution. So the power spectral density graph normalizes our auto power spectrum by the frequency resolution. And what this allows us to do is do an initial comparison of the graphs to determine what energies we're seeing in the signal, irrespective of our frequency resolution. And so I had to turn the blue lines into gray here. So it's a little bit difficult to see. If I didn't turn it gray, you just wouldn't be able to see. But we can see that now roughly when we're taking the power spectral density here on the right, they now have similar levels overall across the frequency range. So the rough energy in the signal, if we're looking at the power spectral density, if you're kind of trying to do, let's say, vibration control and you needed to determine what energies would be present in the kind of shaker profile you're going to need to run, you would utilize a power spectral density to more accurately describe the energy content without getting into the effects that frequency resolution is going to play on the level that you see in your auto power spectrum. And so now I want to get into the analysis of some guitar strumming that I did. So I really like this example. So I took some measurements. It was actually the beginning slide, and this is what I get when I perform the FFT analysis. If I was a better guitar player, if I saw these frequencies, I see we're in the pretty low frequency. So I'm assuming this is a bass, right? I can see there's all of these different frequencies in here. If I was a better bass player, I could say, okay, there's some 55 hertz, a 70 hertz here. I could say, oh, if I'm looking at this, I'm thinking, oh, this is maybe a G chord, for example, or an A chord. If I knew exactly which frequencies correspond to which notes, then I could say, oh, yeah, this is an A chord, G chord, C chord, whatever. That's what I look at when I see this graph right here. But if we actually were to take a listen into what this sounds like, let me make sure I have my audio shared. Share sound. We can actually take a listen to what this sounds like. Okay, so what we actually heard there was it wasn't actually one chord being played at one time. It was actually me playing multiple notes over a series of time. So our 2D FFT was not, well, I guess we're listening to it again. But our 2D FFT, if we're just looking at a 2D graph, it didn't actually capture the transient effects of the sound. And so I want to analyze this utilizing a color map with different frequency resolutions. So a color map is pretty similar to our 2D graph, but now we've got a few different quirks, for example. So we have our time on the x-axis, the frequencies that we're seeing on the y, and then the levels that we're seeing here represented by the color. And so if we look at this with a 4 hertz frequency resolution, it kind of looks a little blocky. It's kind of blending together vertically. I can see that there's these boxes that have some higher levels, some parts with lower, but I can see that we can definitely see that there were three distinct series of notes being played. It looks like this note was being played all of the time, and then it looks like there's some note that was being added in. And then we can kind of see, but in this bottom frequency right here, it's the software isn't able to really pull out which two frequencies were being played because they're so close together. Our frequency resolution is too low to determine what frequencies we're actually seeing right here. So let's take a look with a 1 hertz resolution. With the 1 hertz resolution, now it looks certainly a lot cleaner. I can see exactly what frequencies were being played now, and I can now see here in this region, we can see the two distinct notes that were being played. But what we're seeing now here is that this region kind of got smeared together in time, whereas before we could see that there were a break here and a small break here. Now it kind of looks like this note was ringing out the entire time if I was looking at this FFT, which is not actually the case. So what we're seeing now is with this 1 hertz frequency resolution, we said we had to take 1 second of data. So that 1 second of data is now kind of smearing together because maybe there was only about half of a second right here, where this 4 hertz resolution only takes a quarter of a second. So we're actually able to extract out that there was a pause here, whereas if it was half a second here, it kind of got smoothed together. And we can even see that even more so if we look at it with zero point 0.1 hertz resolution. So now our time is all thrown off. Now we can definitely see exactly what specific frequency was played. We have a lot better frequency resolution, but at what cost? This graph looks literally nothing like what we saw before. If we're looking, we were only looking over the course of 15 seconds. We only have 5 seconds of data right here. I have literally nothing I can do with this data, even though maybe I might be able to have a little bit better of an idea of what frequencies were being played. And so the questions we need to ask ourselves when we're performing this analysis is, well, which of these graphs best captured the frequencies of the notes? Well, even though it hurts me to say that, it would be this 0.1 hertz, right? But it really doesn't do any good job of capturing the transient effects. It didn't capture any of the breaks. It looks like everything was playing the entire time. And so the next question we want to ask ourselves is, which one best captures the changing of the notes? Which one captures the transient effects the best? Well, that would be this 4 hertz frequency resolution. But now with this 4 hertz resolution, now we're seeing some issues in this low frequency region. Maybe we're not able to distinguish out these peaks. But if I were to do analysis of this myself, which of these graphs would I say I would probably go with? Which offers the best middle ground between the two? And that would be this 1 hertz resolution. So these are the things you need to keep in mind, especially when concerning with the amount of time your data and the data you're measuring for. You always need to be cognizant of the parameters that are going into your FFT, your frequency resolution, the amount of time it takes for you to do that, the spectral lines, and the energy that is distributed across them. So I'll give you guys a conclusion right here. So we went over today digital signal processing, a lot of the different acquisition parameters that you need to keep in mind, and leakage. So the FFT allowed us to convert time domain data into the frequency domain. We have our anti-aliasing filters, which prevents the reflection of those frequencies higher than half of our sampling frequency or our band limit back into our FFT when we're performing our frequency domain analysis. And then we saw that leakage is the result of non-periodic functions being analyzed by that FFT, resulting in incorrect frequency domain responses. We were applying a window to our signals to reduce the effect of leakage, but applying a window in and of itself has its own issues. And then at the very end, we saw the different effects that the amount of time and frequency resolution can play when you're looking at data over some designated amount of time. And so I wanted to thank you guys for attending today's webinar. My email is right here in the bottom right. If you have any questions, you can reach out to me.